Alright, so in this video I'm gonna be explaining another important article with the title Revisiting Random Walks for Learning on Graphs. This paper in 2024 will revisit a simple idea for machine learning on graphs where a random walk on a graph produces a machine-readable record. And this record is processed by a deep neural network to directly make vertex level or graph level predictions. We refer to these stochastic machines as random walk neural networks and show that we can design them to be isomorphism invariant while capable of universal approximation of graph functions in probability. We studied the fundamental problems of random walk, show how they can be designed from principles to be isomorphism invariant while capable of universal approximation of graph functions in probability. So we find that almost any kind of record of random walks guarantees invariance as long as the vertices are anonymized. And there is no constraint on the choice of the neural network that processes the records. Second, the universal approximation is achieved if the neural network that reads the records is powerful enough and the random walk covers the whole graph of interest with a high probability. So we define a random walk neural network as a randomized function that takes a graph as input and output a random variable x on the output space. It can be optionally queried with an input vertex v, which gives a random variable x. So random walk algorithm produces L steps of vertex transitions. And then we have a recording function that produces a machine-readable record of the random walk. And then we have a reader neural network that processes record Z and outputs a prediction. It is the only trainable component and is not restricted to specific architectures. To perform graph-level tasks, we sample a prediction by running a random walk on G and processing its record using the reader neural network. So since phi is a function on graphs, it is reasonable to assume that it is isomorphism invariant. Incorporating the invariance structure to our model class would offer generalization benefit. Since x is a randomized function, we accept the probabilistic notion of invariance. We now claim that we can achieve probabilistic invariance by properly choosing the random walk algorithm and recording function while not imposing any constraint on the reader neural network. So this is a random walk algorithm is invariant if it satisfies this. So let us write the probability of walking from vertex u to its neighbor x. And this function c sub g assigns positive weights called conductance to edges. If we use constant conductance, then it is 1. We have unbiased random walk that is used in deep walk. I'll explain deep walk in a different video. So the theorem says the random walk, here, this random walk, is invariant if its conductance is invariant. Of course, these are not related to this implementation. Here is a simple random walk that you see that is created out of this graph. You start with CLS, the first token to indicate it's the first token, and the answer is CLS 41.9. And you can do it for vertex level tasks You can do it for substructure counting. But either you're using node classification or graph classification. So we can compare this paper, which is this method, with the, for example, subgraph GNN. But this is the normalized mean error. So normalized mean error of this method is better than the subgraph GNN. But there is a limitation. Our current main limitation is the cost of performing training and inference with language models, especially on long walks. We believe efficient fine-tuning with low-rank adaptation may help to overcome the issue. The question for future work is whether we can train a language model on a large pseudo-corpus of random walks to build a foundation model for graphs which is language compatible.